Hey everyone, and welcome. Today we're diving into a topic that seems pretty simple on the surface, but is actually a huge reason people fail technical interviews: searching. We're going to break down everything you absolutely need to know about linear and binary search so you can walk into your next interview and just crush it.
So think about it for a second. Searching seems easy, right? Most of us can write a basic search loop. The real trap, and where so many developers get tripped up, isn't the code itself. It's not knowing which search to use and when, and it's completely fumbling the edge cases, especially for binary search. Today, we are going to fix all of that.
All right, so before we start comparing the two methods, let's just get on the same page. We need to be crystal clear about what we're actually trying to accomplish. What is the fundamental search problem? At its core, searching is really just this. You've got a collection of stuff, like an array, and you've got a target value. Your only job is to figure out, is that target in there? Yes or no. Simple as that. The how, well, that's where things get interesting. When we're talking about arrays, it really boils down to two main strategies. You've got linear search, which is kind of like the simple, reliable workhorse, and then you have binary search, the super fast, high-speed specialist. Let's start with the one everybody learns first. Okay, so first up is linear search. I like to call this the slow and steady method. It's not going to win any speed contests, but you know what? It's incredibly reliable. And the logic behind it is, well, it's exactly what it sounds like. You start at the very beginning of the array, and you check every single element, one after another, until you either find what you're looking for or you hit the end. It makes absolutely zero assumptions about the data. Let's just see this in action real quick. Say we're looking for the number 8 in this array. We just start at the top. Is it at index 0? Nope, that's a 5. What about index 1? Nope, that's a 3. Index 2? Boom, there it is. We found it. So we stop and return that index. So, when is this actually the right tool for the job? Well, you'll use it if the array is pretty small, because honestly, the speed difference won't matter. But here's the big one. You have to use it if the array is unsorted. And finally, you'll reach for it when you just need a simple, bulletproof solution that's easy to write and even easier to understand. This brings us to performance, what we call time complexity. Linear search is O of n. Now, all that really means is that in the worst-case scenario, if you have n elements in your array, you might have to make n checks. So if your array has 1 million items, you might have to look at all 1 million of them. And that really gets to the heart of it for linear search. Look, it's not fast, we know that. But because it literally checks everything, it is guaranteed to work on any array you throw at it. Just think of it as your ultimate, super reliable fallback plan. Okay, now let's move on to the star of the show, binary search. This is the fast, the high-performance method, but it's also very disciplined, and it has some strict rules you have to follow. I really cannot stress this enough. This is the single most important rule you need to burn into your memory. If you even try to run a binary search on an unsorted array, the whole logic just completely falls apart, and I guarantee you will get the wrong answer. In an interview, that's a huge red flag. So how does it get all that incredible speed? Well, instead of checking one by one, binary search uses what's called a divide and conquer strategy. With every single check it makes, it gets to eliminate half of the remaining elements. And the thinking process is just beautiful. You look right at the middle element. Is that your target? Awesome, you're done. Is your target smaller than the middle element? Well, then you know it can only be in the left half, so you can just ignore the entire right side. And if it's larger? You guessed it, you ignore the entire left side, and you just repeat that process on the smaller and smaller half. Okay, listen up, because this next section is probably the most important part of this whole explainer. Look, knowing the idea of binary search is easy. It's avoiding the common mistakes and gracefully handling all the weird edge cases. That's what separates a pass from a fail in an interview. So, mistake number 1, we've talked about it, but it is so important it's worth saying again. Trying to run this on unsorted data. The entire logic hinges on the fact that the elements are in order. Without that order, cutting the array in half tells you absolutely nothing. So, rule 1, always confirm the array is sorted first. Now, this one is a bit more subtle, but it's the kind of detail that really shows you know your stuff. The classic way we all learn to find the middle, low plus high over 2, can actually fail. If low and high are really big numbers, adding them together might go past the maximum value an integer can hold, and that causes an overflow error. The fix is mathematically the same, but it cleverly avoids that huge sum. It's a small detail, but man, do interviewers love to see it. Ah, another classic blunder, the infinite loop. This happens if you update your boundaries incorrectly. If you just set low equals mid, for example, you're not actually guaranteed to be shrinking the search space, and your loop can get stuck forever. Just remember this. Once you've checked the middle element, you have to exclude it from the next search. That's why we always use mid plus 1 and mid minus 1.
And finally, we have the loop condition itself. Using while low less than high feels pretty intuitive, but it has a fatal flaw. It fails when the search space gets down to just a single element, where low actually equals high. That last element never even gets checked. By using low less than equals high, you make sure the loop runs that one last crucial time to check that final candidate.
And this slide right here brings it all together. Think of these as the classic stress tests that every interviewer loves. Does your code completely crash if you give it an empty array? Does it work for an array with just one element? Does it exit cleanly when the target just isn't there? All of these problems are solved by correctly implementing those fixes we just went through.
All right, now that we've dug into the mechanics and all the common pitfalls, let's put these two algorithms head-to-head for the final showdown. This table is basically your cheat sheet. Linear search works on anything, it's simple, but it's slow. Binary search, it is breathtakingly fast. Its O of log n time means, get this, you can search 1 billion items in about 30 steps. That's insane. But it demands that sorted array, and it demands very careful logic. The right choice is going to depend entirely on the conditions you're given.
And really, this is the key lesson here. The truly fast solution, the elegant solution, isn't about how quickly you can type out code. It's about pausing for a second, thinking through the problem, and choosing the right tool for that specific job. So, we're going to end on this. The single most important question you can ask, the question that shows you're thinking like a real engineer. It isn't about code at all. It's about the data. Before you write a single line, you need to ask, is the array sorted? That one simple question unlocks everything, and it proves you truly understand the trade-offs. I really hope this helps you ace that next interview.